All right, hello everyone. So today we're working with a linear algebra problem. We've got the following. Find a basis for the column space of A, which sometimes we denote as COLA for shorthand, and the null space of A, null A, where A equals, this is a 3x4 matrix, 3 rows, 4 columns. I'm going to read each row off here. 1, 1, 2, 3 is your first row, minus 2, 1, 3, 4 is your second row, and minus 4, 5, 13, 18 is your last row number 3. Okay, so this is fairly straightforward. There is some computation here. I'm not really going to concentrate on that, as I am assuming that you already know how to reduce row echelon form of a matrix. First of all, you know, elementary row operations, so we're not going to get into that really, but that's what you're going to need to do here. Yeah, so our first step here is to find the reduced row echelon form of your matrix A. And I'm going to call that reduced row echelon form, I'm going to call it a matrix B, and our REFA is, you know, just our shorthand notation for that. And yeah, as you see here, I'm doing a bunch of the row operations, okay, going from one matrix to the next. And at the end of the day, when you wind up with this matrix here, which is B, and B is, let me say what it's equal to here. B is equal to, I'm going to read this off by rows again. Row 1 is 1, 0, minus 1/3, minus 1/3. Row 2 is 0, 1, 7/3, 10/3. And then last row is 0, 0, 0. Okay, now that is our matrix B. And we're going to use that matrix for a couple things. So for the column space of A, we're going to do the following. We're going to note the column positions that have the leading ones in matrix B, our REFA, which is what it's equal to. The basis for the column space of A consists of the columns in A with those positions. So what is it that I mean by that? So I wrote B here in A, and let's look at where the leading ones are, or sometimes we call these pivot positions. That's in column 1. Column 2. Column 1 in A is here, and column 1 in B is, sorry, column 2 in A is right there. And yeah, your basis for the column space of A again, COLA is equal to, it's a set here, it's equal to 1 minus 2 minus 4, 1, 1, 5. And essentially what we're saying is that any linear combination of these two vectors right here, these, yeah, we turn the columns into these vectors, that would make something that's in the column space of A. All right. So we've got that down, and here's what we're going to do next. We're going to find the null space of A. Null space of A is a little more complicated, but not that much. And again, we're going to use B, that reduced row echelon form of A, and we're going to solve the equation Bx equals 0. This will form a basis for the solution null space of A. So you would have Bx equals 0. And what I did here was I transformed that into a matrix. You have the, you know, the augment to the coefficient part, and then you have the answers. The whole thing is the augmented matrix. It's not much for me to do here. It's just, you know, everything's been row reduced. All I need to do is to solve for what I have. And I'm gonna, and what I said here, I'm gonna suppose X here is equal to X1, X2, X3, X4, right? You have some variables that you're solving for essentially here. Call them whatever you want. Just calling them X1, X2, X3, X4 as a column. And what I did here was I took each of the rows in B, in the augmented matrix with B and the zeros are the answers, and rewrote each of those lines. So for example, where I have 1, 0, minus 1/3, minus 1/3, 0, that's like saying X1 minus 1/3 X2 minus 1/3 X4 equals 0. And my second line is equivalent to saying x2 plus 7/3 x cubed plus 10/3 x to the 4th equals 0. And here I just forgot to mention, I'm just making a reference to kind of like where the course starts off when you're solving systems of equations and you're doing row reductions. Each one of those columns represents the coefficients of an equation of a, yeah, so that's why we have what we have here as our equation. And essentially what you're going to do is you're going to solve for, let's say I'm going to solve for x1 and x2. So x1 would be 1/3 x cubed plus 1/3 x4, and x2 is equal to 7/3 x3 plus 10/3 x4. And yeah, x3 and x4 here are free variables. I'm going to say are free, and I can call x3, typically what we do is we call it s, and then x4 is, I don't know, r. We do that a lot of the time, maybe your teachers don't, but anyways, I'm just saying there that, yeah, x3 and x4 are allowed to be any real number, s and r. And essentially here, our solution is equal to x, or x1, x2, x3, x4. And x1 is equal to saying 1/3, and because x3 is s, I'm going to call that s, and then x4 is r. x2 is 7/3 s plus 10/3 r, and then x3 is s, and then x4 is r. And you can rewrite this as a linear combination of basically things multiplied by s and r, respectively. Oh, I'm sorry, I made a mistake here. This should be 1/3, not 1/3 r. Well, not 1/4, excuse me. It should be 1/3 r. So you would get r 1/3, 10/3, 0, and 1. And your bases for the columns, the null space of A, or null A, equals 1/3, 7/3, 1, 0, and then 1/3, 10/3, 0, 1. Okay, and that would be it right there. That is the basis for the null space of A. All right, so that's pretty much how this works out. It's pretty straightforward. I didn't go over the row space of A, but you do this in a similar manner, but you just have to kind of, it's not actually about identifying, though, like you did with the column space. It's actually just more straightforward. Whatever the row-reduced version of your matrix A is, where the leading ones are in the rows, those are the basis vectors for the row space of A. So anyways, I'll hope this helps, and I thank you for your time.